Okay, let's just blast into an example here. I'm going to start with a simple system with a single pole, and we'll sketch the Bode using the asymptotic Bode plot method. And so let's just start with a simple system. G of S is equal to 100 over S plus 30. A single pole at 30 radians per second. And so how we're going to plot this is we're going to look at our rules, and the first thing it says is to factor the numerator and denominator, and so we've done that. And we're going to start with the magnitude plot, and I'm going to look at this the DC gain first, and I'm going to identify a point for us to start with by the DC gain. Remember, we're going to calculate the DC gain with the free s's removed, and we're going to plot that at omega equal 1 second, 1 radian per second. And so, get back here. I lost my page where I was on, so let's do this again. G is equal to 100 over S plus 30. And so calculate the DC gain of that, and we're just simply taking the S is equal to 0, we end up with 100 over 30. So that'd be 10 over 3, and that ends up being equal to 3.33. And now remember, this is in raw or absolute, and so in order to plot it on the Bode, we need to move it to decibel, because remember, this is our axis, our vertical axis is in dB. And so to get to DC gain in dB, we're going to go 20 times the log of the number. And so if you work that out, and I've worked this out before, it comes out to be 10.45 dB. Okay, so that's what we're going to plot, and we're going to plot it at omega equal 1 radian per second. So we come down here. Now we've got a semi-log graph paper in here, and so we've got a log on the x-axis. I'm going to come in here and I'm going to start labeling this 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, and so on. Okay, that should be good for this plot. And we know that at 10 to the 0 is equal to 1. This is equal to 1. And so we're going to plot on this line, our omega 1 line. We're going to plot 10.45 dB. And so I'm going to come up here and I'm going to label this as let's see, label this as 0 dB, and I'm going to label this as 20 dB. Okay, and you'll see why here in just a minute. And this is 40, and this is minus 20 and minus 40. Okay, so that's going to be my axis, and this is going to be a fairly common axis for the points that we or the plots that we deal with. Okay, so now I want 10.45 on 1, and so I'm coming up here about halfway in here, and I'm going to make a plot there, or a point there. That's going to be our starting point for our asymptotic Bode plot. Okay, so now let's go back here. So that's the first thing we're going to do, is plot our DC gain on our Bode plot at omega equal 1. Now, why did we do it at omega equal 1? What is our DC gain? Our DC gain is what it is, what the value, the output over the input, at a constant value of a DC. And now, remember, we're entering sinusoidals, so we don't technically have a DC on this because everything's moving as a sinusoid. And so what we're going to do is we're going to go to a very slow frequency, an omega equal 1, and we're going to say, okay, well, if it's a slow frequency, then we're going to call that essentially DC. And so, so we're plotting that at omega equal 1. Now, go back to our rules in here. Now, we need to figure out the slope of the line. We've got a point. Now we need to figure out the slope as we start moving through here. And our initial slope is determined by whether we have any free s's or not. Okay? If we have no free s's, then our initial slope is 0. If we have an s in the numerator, our initial slope is at 20 dB per decade, sloping up at 20 dB per decade. If we've got a s in the numerator, which is more common as a free integrator, then we're sloping down at minus 20 dB per decade. Okay, so in this case, wow, I keep losing this. I keep losing that. Where is that? There it is. Okay, sorry. We're going to, we have no free s's, and so we're just going to start off with a horizontal line through this point. And so a horizontal line through this point. All right? And so now we're off and running. Now, from here on out, what we do is we look at the next largest pole or zero. Okay? In this case, we only have one pole, which is at 30. Okay? And so we've got a pole at 30. So let's go back to our rules. And if we've got a pole at 30, which is this rule in here, we're going to have a break frequency at that at the pole location, and it's going to go down at minus 20 dB per decade. Okay, so we're going to slope change from the break frequency at minus 20 dB per decade. Okay, so we're going to come in here at 30. So let's see, that's 10, maybe 20, 30. So 30 is going to be right in here. At 30, a frequency of 30 radians per second, we're going to go down. We're going to change our slope to a minus 20 dB per decade. All right, so this is a decade, right? Between lines is a decade, major lines is a decade, and here's 20 dB, right? So what we're going to do is I'm going to go over 1 decade, which will take me to here, and I'm going to go down 20 dB, okay, which will take me to about here, and I know my line has to run through that point, and so I come down through like this, and I have no other poles or zeros, so this is just going to continue on forever at that slope. This is going to be a slope of minus 20 dB per decade. Okay, so that is my magnitude plot for my Bode. Okay, now, in reality, it won't break quite as sharp as this. What we'll see is that it'll come off here and it'll actually go down like this a bit. But this gives us a pretty good idea of what's happening here. Okay, so that's the magnitude plot. Now, let's think about what the phase plot's going to look like. Now, I didn't discuss this earlier, but let's go back to the rules here and see what we see on the phase. The phase plot is determined. The phase plot is determined by the slope of the magnitude plot. The slope of the magnitude plot. And so what we see here is that for each increase in slope, we're going to change the phase. Okay, if we have an S in the numerator, which creates a 20 dB per decade, then we have a increase in our phase of 90 degrees. If we go minus 20 dB per decade, then we go minus 90 degrees. Plus, minus, okay? And so in our case, what we're going to do is we're going to find a shift at A, okay, which is 30, of minus 90 degrees because we've got a minus 20 dB per decade. Now, the rule that you can use to do this, the slope of the magnitude at any frequency, multiply the slope of the magnitude plot by 90 degrees times 20 dB per decade to get the azimuth for the phase. Okay, the slope of the magnitude plot times 90 degrees divided by 20 dB per decade. Okay, so let's go back and see what we've got in here. All right, so our equation is slope times the times 90 degrees per decade, 90 degrees per 20 degrees per decade. Okay. All right. So that's our equation for our phase. So in this case, our initial slope is at 0. Okay. So from negative infinity to 30 radians per second, we've got a slope of 0, and so our slope or our phase is going to be 0. Okay. And so 90 divided by 20, and this all ends up 0. Nothing new there. So let's label this axis 0, 90, minus 90, and let's go minus 180. Okay, you notice I'm labeling in increments of 90 because that's convenient for us. And so initially our phase, our slope is equal to 0, so our phase is equal to 0. So we're going to come out here and we're going to run out here to 90 or to 30 degrees. Okay, and that's going to be our phase. Now, at past 30, we have a minus 20 dB per decade slope, and so we put that in our equation, minus 20 dB per decade times 90 degrees divided by 20 degrees per decade. And of course these cancel out, and what we end up with is minus 90. Okay, so that's going to be our phase through here. So at 30 degrees, we're going to change, and we're going to have a minus 90 degrees. Okay, and so this is our asymptotic phase plot, asymptotic Bode phase plot. Now, it doesn't look like this either exactly. Actually, what we want to do is we're going to come from our pole location, or our 0 location. We're going to step back 1 decade. This doesn't happen instantaneously. So we're going to step back 1 decade, and then we're going to step forward 1 decade to here. And our true Bode would look more like this. Okay. So that would be our Bode plot for our this transfer function. Okay, it could be an open loop, could be closed loop. All we know at this point is it is a transfer function that we want the Bode for. So that would be our asymptotic Bode plots for that transfer function.